Good day, ladies and gentlemen. You are welcome to our lecture number 4 on Eten407, Introduction to Semiconductor Microelectronics. Today we are going to be paying more attention to quantum tunneling. We have already defined this phenomenon in our lecture 2, where we said it is a phenomenon whereby a wave function can pass through a potential barrier. And we said this transmission, that is the passage of wave function through a barrier, is finite. What do you mean by finite? It means whatever will appear on the other side after the penetration of the barrier is finite. It has a fixed value and it depends exponentially on the height of the barrier, as demonstrated here. This is my wave function. We know in classical physics, normally whenever this wave function incident on this potential barrier, it will bounce back, it will be reflected back, because you can see the height of the barrier is much higher than the height of the amplitude of the wave function. So, but in quantum physics, where we deal with a microscopic phenomenon, it has been established from experiments, which we said it those collection of experiments that establish the quantum mechanics itself. It has been established that part of this signal may pass through this barrier and appear on the other side. And the amplitude of the signal that penetrated that tunnel is in most cases much smaller than the incident amplitude because of the reflection and absorption within the potential barrier. This wave function, as I've said, it can, when it incidents on the barrier, it can disappear completely because you cannot see through the barrier, but it will reappear. It will come out from the other side as demonstrated here on this diagram. The wave function and its derivative, if it wants to actually exhibit the property of tunneling, the wave function itself and its first derivative, they must be continuous. Remember what we call continuity in Maths 105, where we deal with limit and continuity of function. It has also been established from experiments that the thickness of the barrier through which the wave function or the waveform can tunnel through is ranging from 1 to 3 nanometer, and of course it can occur less than 1, but for the thicknesses more than 3, the phenomenon is rarely observed. This phenomenon of quantum tunneling has so many essential applications and roles in different situations. For instance, it is used in electronics engineering to design what we call tunnel diode, to design tunnel field effect transistor, that is TFET. It is also used in quantum computing. It is used in designing scanning tunneling microscope. It is also used in other physical phenomena not related to electronics engineering, like nuclear fission, like alpha radioactive decay of atomic nuclei. We even have a quantum biology phenomenon and many more. This quantum tunneling, when it is applied in designing electronics components, it plays a very vital role in minimizing, reducing the size of electronics component, because this tunneling, it can take place even through the insulating layers, which stand for our potential barrier. And if this phenomenon of tunneling is used in designing electronics components, we can come up with transistors that have the thickness of less than 1 nanometer. And you know, the essence of designing integrated circuit, one of them is to minimize the usage of space. So since this tunneling phenomenon can enable us to design transistors of sizes less than 1 nanometer, this brings us to what we call nanotechnology in electronics engineering. And of course, for us to understand why this tunneling actually takes place, we need to go back to our Heisenberg uncertainty principle, which tells us that it is very possible for a wave to have a property of a particle, and of course the particle can have property of wave. So it is based on this theory of uncertainty of the behavior of particles and wave. That some light particles, they can be allowed to pass through a barrier, that is through a space, without actually surmounting, without actually having the energy enough to go over the potential barrier. Now, as we have said, one of the areas of applications of the tunneling is in design of a tunnel diode. Let us look at a tunnel diode and see how it works. This diode is called a tunnel diode. Sometimes it is called a Saki diode. The reason why it is called tunnel is because it is using the principle of quantum tunneling. And of course, the reason why it is called sometimes a Saki, it is because the scientist who worked on inventing the principle on which it operates, that is Leo Esaki, his name is used to call this diode as a respect to him. This man earned the Nobel Prize for Physics in 1973 for this work in the area of tunneling. And it is a semiconductor device that has two terminals. We know already diodes, normal diodes, they have anode and the cathode. And the difference between this one and the normal diode is that it has a very fast operation, because it can operate at frequencies ranging to microwave frequencies, that is up to the gigahertz range. And this fast speed of the tunnel diode is made possible from the effect of this tunneling, where the electrons can cross from the anode to the cathodes, or from the cathode to the anodes, depending on whether we are forward biasing it or reverse biasing it, with application of very small voltage as compared to the normal diode. Therefore, the passage, the transmission of these charge carriers will take place at a very higher rate, and that is why it has very high frequency, ranging to microwave frequencies. And the design of this diode is made in such a way that the doping is very high as compared to the normal diode. For instance, this is the diagrammatic explanation of how it works. We know in normal diodes, the movement of electrons from the valence band into the conduction band, in between them we have what we call the forbidden band, where we have to supply an energy called the energy band gap, or the energy gap energy, for us to be able to move electrons from the valence band into the conduction band. In principle, we are saying that these are the three layers. This is our conduction band, this is our valence band, and this is the valence band, and this is the band gap, or the forbidden band. As we know, for us to be able to move electron from the valence band into the conduction band, you have to apply an energy that is enough to be more than the height of this potential barrier, which is our energy gap. But on the other hand, if we look at it from the point of view of tunneling principle, you find that this energy gap is completely eliminated. That is to say, the electrons can easily move from the valence band into the conduction band without supplying this energy gap. And this is demonstrated here. That is, the electrons can easily pass through the energy barrier without overcoming the height of that barrier. And this diode, as I have said, because it requires a very small amount of energy for the electrons to move from the valence band into the conduction band, definitely it requires a very small voltage for its operation. And this junction diode, it also have another property which is different from the normal PN junction diode, and that is what we call the principle of negative resistance between two values of the forward voltage, as we are going to see. And this is the pictorial diagram showing the tunnel diode, and as you can see, it is entirely different from our normal a PN junction diode. And as I have said, it is made with a very high level of doping, sometimes more than 1,000 times the concentration of the dopant as compared to the conventional diode. And of course, this level of doping is responsible for giving a very large number of majority carriers. And because of this large number of majority carriers, you find that they outnumber the minority carriers. Therefore, the recombination that takes place in the joint, that is where the P and the N junction meet and create what we call the depletion layer. In this tunnel diode, the size of the depletion layer is very, very narrow, sometimes more than 100 times less than the conventional diode. And as I have said, the reason why it has this thin depletion layer is because of the level of the dopant concentration. In the normal diode, we have dopants like 1 to 10 raised to power 8, but that is when we are using silicon or germanium. But in the tunnel diode, the concentration is increased to around 1 to 10 raised to power 3. As you can see that the ratio between this and this is almost 100,000 times. So the concentration of the foreign materials introduced into the P end and the N end makes it possible for the depletion layer between the two to be very narrow, so that without even applying a significant amount of voltage, the charge carriers can be crossing the junction and creating the current that is responsible for its operation. This effects of this tunneling that happens in the tunnel diode is what we call the reason why we call it a tunnel diode. And as I've said, this is the IV characteristics of the tunnel diode. That is the relationship between the voltage and the current. In the normal diode, if we can remember, whenever you start increasing the voltage from 0, let's assume we are using silicon, you have to reach a value of around 0.7 before the voltage starts rising exponentially. And if we are using germanium as the base material, it requires around 0.2 volts for the conduction of electrons to start. But in this case, you can see that whenever the voltage starts rising from 0 level, the current will also start increasing. And the reason is what I have just explained. We have high level of doping, and the thickness of the depletion layer is very small. Therefore, the potential barrier is very small. Therefore, a very small voltage can create corresponding value of current. As you continue to increase this voltage, you reach a point that is where we have the peak value of the voltage, and from that, whenever you create any increase in the voltage, the current will start decreasing, and this is what we call the negative resistance region. You can remember, according to Ohm's law, whenever the voltage increases, the current is supposed to increase. But in this operation of the tunnel diode, there is a level of voltage after which the current will be decreasing as the voltage increases, and that is what we call the negative resistance region of tunnel diode. And the existence of this phenomenon gives us ability to also operate the diode even in reverse bias mode. Therefore, it is excellent conductor even in reverse bias mode because of the level of concentration I've just discussed. Then you reach a point where you have our valley point. That is where we have the minimum value of the current as the voltage increase. If you go beyond that, your diode is no longer operating as a tunnel diode, but it will be operating as normal diode, increasing exponentially with respect to the value of the voltage. And these tunnel diodes, normally they are made either using germanium or using gallium arsenide, that is a compound semiconductor. And the reason why it is used, these materials are used, not silicon, is because their highest peak voltage to valley swing points. This is what I'm saying. As you can see here, my voltage and current are increasing, and here I have my voltage increasing while the current is decreasing. So this change in value that creates corresponding decrease in the current is what we call our voltage swing. So using either germanium or gallium arsenide will make this phenomenon to take place higher. And the ratio of the high peak current to the valley current, that is the current at point B to the current at point C, the ratio of these two is the one that quantifies the maximum voltage swing. It will tell us the alternation in the voltage that will give us the difference between these two currents. And it is responsible for our negative resistance, as I have already explained. The electronal diode has so many applications. For instance, it is used in high-speed operation due to the fact that the tunneling effect takes place at a very high speed, the speed of light, 3 times 10 raised to power 8 meters per second. And it has an advantage of low cost. And also it has another advantage of low noise, because the tunnel diodes are used at a very high speed switches, therefore it doesn't have any noise. And of course, another advantage of the tunnel diode is that it is used for high frequency operations up to the microwave range in gigahertz, and that is why we use the tunnel diode to design a microwave oscillators. And it is also having what we call the environmental immunity, that is, it don't have any emission that causes problem to the society. It has low power dissipation, another advantage, and it is very simple in fabricating, and of course it is more durable. It has more longevity than the conventional diode. Despite all these advantages we have seen, it also has some disadvantages. One of them is low output voltage swing, what I explained between point B and C in that IV characteristics. Another disadvantage is that because the two-terminal device, that is the PN junction diode, which is a tunnel, there is no isolation between the input and the output, because I told you the level or the thickness of the depletion layer is very, very small. So the absence of this isolation, seemingly, not really, it causes some misbehavior from the diode. Now, the diode is used also in so many other applications of electronics engineering. It is used for switching, designing switches for on and open systems. It is used in amplifier. It sometimes behaves just like what the transistor does, that is to amplify signal, and also it is used for oscillation to change DC to AC signal. The past response of this diode, the frequency you have just mentioned, it is used in designing so many high frequency components of electronics. And the tunnel diode also, it is used as a logic memory storage device because of this ability to switch between the peak valley current and the low valley current. It is also used in FM receivers for transmission of radio signals. So with that said, let us look at the other component, that is a tunneling field effect transistor, that is TFETs. This TFETs operate on what we call the band-to-band tunneling. As we have seen in the PN junction tunnel diode, we have seen that there is an elimination of the forbidden gap, or the band gap. So here, the tunnel field effect transistor operates on what we call the band-to-band tunneling. And for this band-to-band tunneling to occur, then the valence electrons in the semiconductor must be able to pass through directly into the conduction band without what we call the traps. And these traps is nothing but applying enough voltage to overcome the potential barrier between the valence band and the conduction band. In this case, it will take place without application of those voltages, similar to what we have seen in tunnel diode. This band gap is now acting as our potential barrier, and the particles are able to cross it because of the tunneling effect we have already explained. And as we have seen, the electron can travel from the valence band to the conduction band without absorption or without emission of the photon in direct tunneling. That is, we have two types of tunneling taking place on a tunnel field effect transistor. If we are looking at the direct tunneling, the electron can just pass from the valence band into the conduction band without absorption or release of energy. That is, without use of any energy to overcome the thickness of the barrier. And if that happens, we call it direct tunneling. And we have what we call indirect tunneling, where the electron need to have some energy. It has to absorb some energy or to emit some energy for it to be able to move from balance band into the conduction band. Therefore, in essence, we have two types of tunneling in tunnel field effect transistor: direct and the indirect. So in the indirect, we have what we call the direct band gap, that is E subscript tau. This is a constant, and if this direct band gap energy is much bigger than the indirect band gap energy, which is Eg, then the indirect tunneling is the one that will be taking place, because this energy is much more than that of the indirect. And in this direct tunneling process, indirect tunneling process, the direct also takes place, but it is very negligible. Therefore, the major tunneling is direct, where the indirect is negligible. But when the indirect is the highest, then the direct should also be negligible, because the probability for the electrons to pass from the valence band into the conduction band is increasing rapidly whenever the potential barrier decreases. And when the potential barrier increases, the probability will decrease. In this field effect transistor, the tunneling can take place if the thickness of the barrier between the valence band and the conduction band is within the range of 1 to 3 nanometer and smaller, just like in the tunnel diode. And if that happens, we'll see that all the operation of the gate is now going to be controlled, not by application of the voltage that close the gap or open the gap as in the case of original FET, but rather it is the tunneling that is enabling the charges to move from the source into the drain through the gate without application of the voltage at the gate, as in the case of normal FET. And in the normal FET, we require a voltage of around 1 volt for us to be able to open the gate so that the charge carriers can move from the source to the drain. But in the tunnel FET, you find that it reduces to as low as 0.2 volt because of the effect of tunneling. And if that happens, it reduces the consumption of power of the T-FET by up to 100 times or more than 100 times, because the tunneling effect is taking care of the supply of voltage that causes the movement of charge carriers from the source to the drain. And if this transistor, because of its potential for reducing the power consumption and of course the size, if it can be used in very large scale integration ICs, it will definitely significantly improve the performance of the power. That is, it will reduce the consumption of the power of integrated circuit, which is one of their major problems. And of course, it has advantage of reducing the power consumption, but it has one fundamental problem, one challenge. And the major challenge of this tunnel FET, it has limited on current. The amount of current that it conducts when it is on is very, very much smaller compared to the typical field effect transistor. And this low current can be addressed. That is, it can be improved if we create higher doping levels. That is, if we increase the concentration of the foreign materials introduced into the T-FET. This diagram shows the typical diagram of the T-FET. As you can remember, in normal FETs, it is either N channel or P channel. That is, our source and the drain, they must have the same polarity. If this one is P, the other one should also be P, while the gate between them is the one that will be controlling in such a way that either to operate in enhancement mode so that it will allow sources to move from, charge carriers to move from the source to drain, or in depletion mode to close the gate so that no movement. But in this case, our source is heavily doped P-type, then the drain is heavily doped N-type. So this is a major difference between the normal FET and the T-FET. While the gate between them is just serving as the channel where if the tunneling is having enough probability for sending electrons or charge carriers from the source to drain, then this one will ultimately be operating as if it is a PN junction diode. And this is the graph showing the stiffness, that is the height of the energy barrier for the TFET to conduct. As you can see, this gap is telling us the requirement of amount of energy that will be used in order to be able to push the charge carriers from the source passing through the gate to the drain if the TFET is off. But whenever it is biased and it starts operating, you see that this wide gap will automatically close, so that the electrons will now be tunneling from the source to the drain, and hence the TFET will start operating. In the normal MOSFETs, the source of carrier injection is the thermal injection. What we mean is that we apply a voltage, and that voltage is responsible for creating a current that would somehow rise the temperature, therefore giving the electrons more energy for them to be able to move from the source to the drain. But in the TFET, that is the tunnel FET, we use what we call band-to-band tunneling. We don't need any thermal injection for the energy or for the electrons to move from the source to the drain, but it is the tunneling effect that will allow them to close the gap so that the charge carriers will be moving from the source to the drain. The diagram we have seen here is our figure 1, and the first one, as I've said, shows the schematic diagram or the block diagram of the TFET, whereas these are the graphs when it is off and when it is on, as I have just explained. This TFET also is called arm bipolar device. By arm here, we mean it can operate in two modes, just like amphibian animals. It means it will show P-type behavior when the dominant charge carriers are whole, and it can show N-type behavior when the dominant charge carriers are electrons. And as I've said, the biggest challenge of this TFET is low on current. The current that passes when it is on is very, very small. Whenever you want to increase it, sometimes you decrease or you worsen the off current, because normally the off current is supposed to be 0, but actually we have always thought we have what we call leakage. So whenever you try to increase the on current, which is small, and it is a problem, you may end up increasing the off current, which will cause another problem. So you have to strike a balance by doing what we call optimization. Now, what are the advantages of the TFET? It has low switching slope, that is a very small voltage will make it to switch on and start conducting, and it has low power requirement, and it has better temperature strength. And its application ranges from digital switch, ultra low power electronics applications, because it requires very low power, as we have just explained, and it is also suitable for applications that have low standby power logic, and that is also it has to do with the consumption of power when the device is not operating. And it has advantage of low power specification also in ICs, and it is used in many integrated circuits. So ladies and gentlemen, this is the end of today's lecture. Thank you very much for your time. I advise you as usual to watch over and over again till you understand. Thank you till we meet in our lecture number 5.